Welcome our first speaker, which is Yiannis Kaznessis from Minnesota, and he will tell us about closure scheme for chemical mass equation.
That's good. Thank you. Good morning. I'm going to start by thanking the program organizers. It is a distinct pleasure to be able to work here for a few months. Dave Anderson for the chance to present some of our work to this workshop. It is a pleasure to present to this group, and I'll start with what is now a near canonical tradition of workshop presentations, thanking my group members. I've been fortunate over the years to have a number of brilliant students at Minnesota. Howard Salis was the one that a dozen years ago started most everything that I will discuss today. Then Vasily Sotiropoulos, John Thompson, Tony Hill, and others helped us progress in our work. Patrick Smedbeck was the one that really closed a lot of the things that we have been working over the past, 12 years, but opened at the same time new avenues for new students to explore, like Michalis Vilisidis is doing right now. I'll discuss 3 vignettes, going back again a few years and then all the way into work that we do today. So my students, just very briefly, let me just say that my students and I have been working on topics of interest to a lot of you that you have discussed here for the past few days. I mean, we've worked on algorithms for stochastic chemical reacting systems that use hybrid stochastic, continuous stochastic, discrete type of modeling formalisms. We have done work on sets of stochastic differential equations, adaptive time stepping techniques, model reduction methods. We have developed software that we've made publicly available, and we've used these models to guide our experimental work, synthetic biological related type of work. I'm fortunate to present next Tuesday, this coming Tuesday, in the regular seminar series, and I'll be discussing some of the work that we do in the lab that is guided by these types of experiments. So this is my slide, like Mustafa was saying yesterday, that will set the notation that we use for chemical master equation. So for all the work that we have done, our sites have always been on the CME. X is the vector of the counts of molecular species in a homogeneous, isothermal, isochoric, well-steered vessel reaction volume. So we have reactions happening in there, and for arbitrary reaction kinetics, we can come up with certainly the reaction propensities, and with the reaction propensities, we can set up the master equation. The master equation is near impossible to solve. It's impossible to solve directly for arbitrary reaction networks that include nonlinear reactions. So what we have done is, instead of trying to solve the master equation itself, we looked at the moments, the probability moments of the master probability in the master equation. So we can in principle come up with equations that evolve the mean, the variance, the skewness, the kurtosis, the higher order moments, and in principle, the time evolution of the moments, of the probability moments, will give you the same exact information as solving the master equation for the master probability. This is certainly nothing new. I mean, a number of groups have been discussing writing the master probability equation in terms of moments of the probability equation and following the time evolution of the moments instead of the actual probability distribution. This is just an arbitrary selection of a few groups that have done work more recently on deriving moments for probability distributions in chemical reaction networks. What Patrick Smedbeck did was develop an algorithm that allows us to very quickly come up with equations, moment equations, for arbitrary reaction networks to arbitrarily large order. So we can very quickly, using a z-transform, using this generating function, if you start taking derivatives recursively, very quickly you can come up with the factorial moments, right? The first moment, the second moment, the third moment, the 1000th moment, the 5000th moment. Arbitrarily large matrices is what we can generate with Patrick's algorithm fairly quickly. And we can go back and forth between factorial moments and polynomial moments, which is we and others use more often. I mean, there's just a simple similarity transform between the two. So we have an algorithm, and I'm not going to go into the details of this algorithm, other than to say that we can now, again, write equations for moments of reaction systems, and this is just the simplest example. A gives B. This is a linear reaction, right? So you, in principle and in practice, you only need two moments. You need the mean of the number of molecules of your reactant species and the variance. And if you have that, then you can reconstruct the probability distribution, which is, in linear cases like this one, simple cases, it's going to be a Gaussian, right? A Gaussian probability distribution. So you indeed only need these two moments to explore the stochastic kinetics of this system. Well, what happens when you have nonlinear reactions? Let's look at 2A gives B reversibly. And in this case, again, the algorithm is there, derive the master equation, derive the moment equations, and just to give you, like a sense of the trouble that everybody has been running in, you write the equation for the mean of the number of molecules of your A species, right? And immediately you see that there is the second order moment on the right-hand side. You write the equation for the second order moment, and the third order moment comes in. You write it for the third, the fourth one comes in. You write it for the 10th, the 11th, and the 12th come in. There's a closure scheme challenge, right? So these equations are infinitely long, and there's an infinity of ordinary differential equations that we can have, and they never close. And it absolutely does not make any sense, right, to just say arbitrarily, you know what, I will truncate them. Let's say, like, I'll only go to the fourth order, and then the fifth one, I'll just say that it's 0 and just forget about these terms. I mean, you take any number, right, larger than 1, and you raise it to a power of 5. That number is much larger than that number of molecules raised to the power of 3 or 4, right? So these terms are actually significant, like in the set of equations, and you cannot just simply truncate the moment equations. So we have the moment closure scheme, and in order to keep things concise, right, because as we increase the number of moments that we use, we can write for any reaction network, we can write the moment equations in this form, right? So mu is the vector of any set of lower order moments that we will use to describe the probability distribution of the reaction network. And m prime is just the higher order moments that creep in the moment equations, right? For nonlinear systems, for nonlinear reaction systems, right, you can show that this A prime, right, has non-zero elements. Okay? This is the closure scheme challenge that everybody faces in the field. Okay, so everybody then, and again, this is nothing new. I mean, people have been trying to do this for a number of years, and again, this is just an arbitrary selection of some work that has been done in the recent past on starting with master equations, going into moment equations, and then always looking for this type of approximation, right? Just trying to write the higher order moments as functions of the lower order moments and close the scheme. Okay? So this is what we did. With Patrick's algorithm, we were able to calculate, to very quickly develop these equations, these moment equations, and we started calculating high order moments here for reaction networks. And one observation that was interesting to us was this, that as we increase the order of the moments, we were calculating the correlation functions of moments, right, for reaction systems. And what we started observing fairly quickly is that the higher order moments relax much faster than the lower order moments. And indeed, the correlation functions, are congruent, normalized correlation functions, appear to be having the same type of information in reconstructing the probability distribution. And in any event, higher order moments decay to near 0, right, at very short time scales. And this told us that they cannot be playing an important role in reconstructing the actual probability distribution, right? And from a physical point of view, it does not make sense for a finite, however large, right, but for a finite system to require 10 moments or 12 moments or 20 moments in any type of situation that we face. It just doesn't make physical sense, right? This allowed us to suggest, right, that the higher order moments have no information, they stop containing non-redundant information about the underlying distribution fairly quickly. And ultimately, this led us to the closure scheme that we proposed, the zero information closure scheme. So with lower order moments, having a set number of lower order moments figured out, determined, we can find the distribution that maximizes the information entropy. So there's this information, the Shannon information entropy. And we have to do this, right? We have to find the probability distribution that maximizes the entropy, but do this under the constraints of known lower order moments, right? So these equations must be satisfied, right? For the mean, again, the variance, the skewness, the kurtosis, the m order moment that we need to describe the probability distribution, right? So with m order, up to m order moments known, this becomes a constrained optimization, right? And ultimately, the algorithm boils down to figuring out, determining the Lagrange multipliers in this constrained optimization. Again, I mean, using entropy maximization techniques is nothing new in physics and in chemistry. So it's straightforward to show, right? It is indeed trivial to show that the probability that maximizes the entropy of a reaction system is just this exponential, right? With the lower order moments that we use up to order m, right? With the Lagrange multipliers as the coefficients. When we calculate this probability distribution, we can go now and start calculating the higher order moments, right? M1, right? M plus 1, M plus 2, M plus 3, right? Whichever ones we need, to just close the set of moment equations. So assuming that the higher order moments cease to contain this non-redundant information, we were able to close the set of moment equations. So how does this work? Just schematically, the algorithm, we start with an initial condition for all the moments that we need in the set of equations of moments that we have developed. And the easiest one in terms of starting initial conditions is to assume that there is a delta function, right? So with a delta function, we have the lower and the higher order moment values, right, at time 0. And the indices here are just time steps, right? So at the first time step, we know this, so we can calculate the derivative from the moment equations. And then when we have the derivative, we can go and calculate the lower order moments, right, at the next time step. Now, with the lower order moments at the next time step, we can run the optimization, constrain optimization, maximize the entropy, right, and calculate the higher order moments, right, at time step 1. And now we have, again, a set of mu1 and mu1 prime, right, that we can go back and repeat, right? And we keep on doing this for time step 1, time step 2, and I'm just showing you, the first moment, the average of this reaction network that we're using in this example, and then how the probability can be reconstructed from the moments that we calculate. So this is roughly how the algorithm works, and we can of course go now and start using this in a number of different examples. So the reversible dimerization, we can look at the dynamics, right, of the system, different initial conditions, and what we start doing is just changing in this case, the equilibrium constants. But what we're doing is we're solving the moment equations, and in this case, it's just up to 4th order zero information closure scheme. So we use the 4th order moments that we know, and then we calculate the 5th one using the optimization. And we always, right, run SSA just to compare the two, and just for sanity's sake, right, just make sure that what we calculate is correct. And indeed, we can see the lines, the straight lines are the closure scheme results, and the circles are the SSA trajectories, and you need a million trajectories to come up with this type of of accuracy fairly quickly. Okay, so we've done a number of examples besides this very simple one. The Slogel model, right? The Slogel model is just a canonical toy model. I mean, it's an interesting one because there is a bimodal distribution that appears here for ranges of kinetic constants. So how many moments do we need here? Certainly, 2 wouldn't do the trick, right? You cannot just fit this type of probability distribution with 2 moments. We saw, and I'll discuss this in terms of the algorithm and how we figure out the number of moments that we need. Ultimately, it's an empirical calculation, right? I mean, we have to just keep on increasing the order of moments that we use and see up to beyond which point there's no improvement in the accuracy. So 2 moments, 4, 6, 8, 10, 12 moments is what we need to come up with an accurate estimate of the probability distribution of the Slogel model. So here the mean, the big one, the variance of the x, right? So this is a one-dimensional toy problem. So there's only one molecule that we need to follow. Mean and variance for x in the Slogel model. The circles here are again the results from SSA, and we get the straight line for the average, right, to be the result for the 12th order ZI closure scheme. Here what we do is we start with so this moves in time, right? Red is the past, and then we're moving right into time, changing colors, ultimately reaching a steady state with the blue here. So we start with this delta function in the back, and then the system evolves. So we can do this in time, and ultimately we get this probability distribution at steady state. Then the circles are the result for the SSA. Yes.
How much faster is the 12 order your scheme with all the optimization compared to just doing the SSA?
It is not. Let me just tell you why. So for dynamics, right, we can calculate dynamics accurately. We can get the probability distribution accurately. But I would not do this for dynamics quite yet. So simply because every time step, right, we have to run an optimization scheme, right? And I do not know how to run good optimization schemes. Really what we do is we use Newton-Raphson, right, to calculate the Lagrange multipliers. Very slow. I mean, there are a couple of students in my group right now who want to spend some time trying to figure out ways to optimize this, just stochastic annealing type of methods. They're gonna work on this, and they will see very quickly, I think, that that they shouldn't be spending their time on this. Just say this. So I would never suggest.
The steady state itself, is that faster?
Let me. Yes, that's my next slide. So in terms of dynamics, right, starting from arbitrary initial conditions and closing the scheme, right, and following the evolution of the moments, it does not make sense to use this compared to SSA, compared to hybrid methods, right? I mean, that simply does not make sense at this point. But there are a number of people here, who I hope can help us at the very least, just go beyond Newton-Raphson. Of course, yes.
Can you just go back to the other side? I just wanted to.
This one?
Yeah. So obviously, when you begin, it's not bimodal. So.
It is not. It's a delta function, as a matter of fact.
Yeah, exactly. So when it starts up, so what do you see in the moments? Like, is it that the moments go from 0 to something really big and wait there for until the time comes that it starts to become bimodal?
So in this case, right, and again, it depends on how you start the initial condition. Delta function means that only the mean, right, has a value, right? It's the value, at whatever it was, 25 molecules that we have here. And the rest of them are 0. And immediately, the thing just spreads up, right? The second order starts increasing, the third order starts increasing, right? And ultimately, the 12th order starts becoming relevant, right? And they become this bimodal distribution.
Do you think along the way you can decide if you want to add a moment or not?
In principle, I'll say that adaptively we can do this, right? Going back and forth. No, it's too much. It's better to run an SSA, get a very quick sense of where you are in terms of the probability distribution, its shape, and the moments that we would have to use if we can do this, right? In higher order or multidimensional systems. Multidimensional, I mean 2 dimensions or 3, right? Because we're going to have this problem, of course, where you increase the number of degrees of freedom, right? It's going to be with 2 degrees of freedom, high order moments you have like x and y, right? and then you have x squared, y squared, but then you also have x times y, right? And then, so there are all these combinations that very quickly, numerically, will be very hard, right, to solve back into the optimization scheme. Going back to what you suggested, not dynamics, but steady states, right? So I can calculate the steady state. Inside the reaction network has all the information that I need, right, to come up with its steady state without having to run SSA, without having to run the dynamics here, the dynamic evolution of the system. I can find the steady state. Just the input is here, this expanded matrix, and out come the moments at steady state. So this allows us now to very quickly, right, scan steady states as spanning kinetic constants or equilibrium constants. In this case, I'm just showing you, this is the straight line. It's every point here, right, is an equilibrium calculation for this reversible equation, where we have thousands of steady state distributions really determined in seconds. So we span 6, 7 orders of magnitude for the equilibrium constant, right? And for each one of these equilibrium constants, we can come up with the mean and the variance of the number of molecules of A. Its square here, right, is 1,000,000 SSA, right, trajectories, right, to just come up with the steady state of this particular system. Yes.
But is it 1,000,000 SSA simulations or just 1,000,000 times finding the null vector of a big matrix?
So this is 1,000,000 SSA here, right? But the squares here are results from SSA. The line, right, is the result that we get from using the ZI closure scheme, right, near continuously over the equilibrium constants that we have. Okay. So very quickly we can do this with the ZI closure scheme. Calculate steady states. We do this with the Schlogo model. We do this with Michaelis-Menten. We do this with a number of different examples, right? Very quickly scan kinetic constant values, equilibrium constant values. Yes.
Okay, in this case, you know the steady state and whatever. But when you don't know and you have a variety of different parameters, and you want to understand how the steady state looks like, how do you know when you have to?
Well, you're gonna run
the number of moments.
You're gonna run the same problem, you know, with any type of multi-dimensional numerical optimization scheme, right? You will have to start with an initial condition that is closed, right? So again, my students have been arguing that they want to do this, right, where they start with arbitrary initial conditions for the probability distribution, right? And they expect that they will be able to find the probability distribution quickly and accurately. I don't think so. But what I do tell them is that what they should do is just run SSA quickly, right? Just a few trajectories, not sample the probability distribution accurately using SSA, but use that, okay, just to get an information, just a starting point, right, to fit into the ZA closure scheme. And the moment that you do this, right, so if you find, for example, a point right here, right, with ZA closure scheme, and then you start perturbing the kinetic constants or the equilibrium constants, you already have that previous initial condition to use. It doesn't make sense, right, to use arbitrary initial conditions for every single one of these points, right? So then you can just do this here very quickly, starting with a smart initial condition. Okay, so
one question. So it's a number of moments that you need, right? So you have here a 12 order.
yeah.
So is that really due to sort of this bistability that's present in the Schlegel model, or also perhaps of this trimolecular reaction, right? I mean, so you could in principle sort of rewrite this trimolecular reaction.
Well, it's the bimodalities is what we're trying to capture here, right?
So no, I understand, but I mean, is this so what's the origin of the fact that you need so many moments? Is that really just the bimodality, or does also the fact that you have a trimolecular reaction, which is playing a role?
Well, the trimolecular reaction is what leads you into the three solutions in the deterministic, right, and the bimodality. It's the bimodal distribution. If you give me a bimodal distribution, right, any bimodal distribution, regardless of where it's coming from, I will say that you need 8, 10, 12 moments to capture that accurately. Okay, so let's go a step further, right? So we have steady states. We can just scan things quickly. Toy models, right? Simple models, right? But what can we do in terms of an analysis of steady states, right? This is certainly a field, right, where in deterministic systems, there's work going back 100 years, right? So you have a set of ODEs. You can find the steady state. If the system is not linear, you can linearize around the steady state, find the Jacobian around the steady state, look at the eigenvalues of the Jacobian and make comments, make statements about the stability of the system based on the eigenvalues, Lyapunov exponents, a lot of people call them in the literature, right? If they're negative, the system is stable. If there's imaginary part, there will be oscillations, right? Can we do something like this now for stochastic systems? And the answer is yes. With the closure scheme, right, we can start with the moment equations, right, and read steady state and linearize around steady state, right? We do this numerically, right? But we can calculate a Jacobian, right, at the steady state. And really the relationship is one that comes naturally from the optimization. These are the Lagrange multipliers. And it's a very simple, fairly straightforward way of calculating the elements of a Jacobian, right, at the steady state for the moment equations. And then what we can do with this is look into the eigenvalues of the Jacobian and make statements about the stability. What we can also do is look at the correlation functions of the moment equations. We can write something like this with the Jacobian. This is the time derivative of the correlation functions. Then the correlation function is just simply going to be an expansion with exponentials with the eigenvalues of the Jacobian being the exponents, right? And again, for sanity's sake, we will always run SSA, always try to compare to SSA. One more thing that I wanted to do was look into fluctuation dissipation like type of relations. So any system at steady state, right? So you have a system, a reacting system at steady state, and you perturb it a little bit, right? You change the kinetic constants, you change the input, and it will move to a new steady state. Right? This response function, right? The dynamics of the response going from one steady state to another steady state, according to the fluctuation dissipation theorem, right? That response, right? The dynamics is congruent to correlation functions of fluctuations at the steady state itself. Right? That's what the fluctuation dissipation theorem says in statistical mechanics. Right? So what we do is we go in, right, find steady states, and then perturb parameters, move to new steady states, and we can do this with SSA certainly, right? So we can calculate these response functions. So here's some results. The reversible dimerization, calculate the Jacobian, calculate the eigenvalues. This is just the eigenvalue, the dominant eigenvalue for the mean of the number of molecules of A. And we do this a couple of ways here, where we change the kinetic constant K1. K2 in the blue line is always equal to K2 is equal to K1, and then we keep K2 in the red line just constant. We always find, of course, negative eigenvalues, right? And the eigenvalues, of course, I mean, it's been discussed for ergodic systems. The probability distribution, right, is going to be stable. What the eigenvalues tell us, right, is how fast, right, the dynamics of the system change, how fast the moments fluctuate inside the system. So we do this then for again for SSA, and we do this with the fluctuation dissipation with the response function. And we do this again with multiple kinetic constants, and we see that the results certainly agree perfectly well for this simple example. Here's in more detail what we do with the fluctuation dissipation relations. So we have a steady state, right? So we have a steady state here, and K2 is 1 inverse second. And at time 2, right? So this is just following the system dynamically, right? We go in and we change the kinetic constant from 1 inverse second to 1.05, right? It's 5% change here, right? And immediately the system will go to a new steady state. And the response function we normalize from 0 to 1, right? And at time 3 then, right, it reaches this new steady state, just we switch back the kinetic constant, right? And the system relaxes back to its original steady state. So this response function, right, of course, is the one going up and the one going down are inverse, right? Normalized, are congruent to one another. And what is interesting to me is that they are both congruent to the correlation functions that we calculate using the Jacobian at the steady state. The Slogel model, we again calculate the eigenvalues from the Jacobian. This is the dominant eigenvalue for the mean of x. We see this parabolic profile here. Things slow down, so always negative eigenvalues, but things slow down as we change this kinetic constant. And you see that as we change this kinetic constant, the system goes from becoming unimodal, bimodal, right, to going back to unimodal. So what happens here is that there's this additional time scale, right? So there are the time scales, right, of the system exploring each one of the modes. But when the distribution is bimodal, there's this additional time scale of the system going from one mode to the other, right? So this is what slows down the dynamic behavior of the system at steady state, and then its response as well, at non-steady state. And these are the correlation functions for multiple kinetic constants, for the average of the number of molecules of x. And you can see how the correlation functions slow down as we go from uni to bi to unimodal probability distributions. Okay, so we have the steady states. We can calculate those very quickly. Okay. Of course, there will always be numerical dependencies on the initial conditions, right? Certainly, if we go and we start looking at two-dimensional, three-dimensional problems right now. We have this issue, of course, with dimensionality. If you go to larger systems, the state space increases. Everything that has been discussed here is applicable here as well, right? But we do have a tool, right, to fairly quickly come up with steady states. And again, I'll say this: it's okay, right, to cheat a little bit, go with SSA, start with an initial condition, and then use that as a starting point to scan kinetic constants or equilibrium constants. But then we have this tool now that analytically, near analytically, allows us to talk about the stability of this systems, closed systems, certainly, right? And we come up with the eigenvalues of the Jacobian at steady state that allows us to make statements about the stability and the dynamics of the system. The third vignette, which is work that we're doing right now, we're looking at the Slogel model, and we want to ask the question that Tom has asked 40 years ago. What happens to the probability distribution systems, the probability distribution of stochastic systems as we increase the size of the system, right? How do stochastic modeling formalisms match deterministic ones, right? And the canonical point of view is that a stochastic system, as you increase the size of the system, will reach a solution, right, that matches the ordinary differential equation solution. Okay, it's interesting to see what happens with the Slogel model. The Slogel model, which has a bimodal distribution, which the deterministic system, right? So it's this simple equation, right, third order equation, right? You set this to 0, right? You find three solutions, right? Two of which are stable. Like here, the red dashed lines, and then the one is unstable. Okay, so just simple stuff in terms of the ordinary differential equations. If we have a small system, right, that is under the influence of noise, maybe we can run the ZA closure scheme or SSA and find this probability distribution. You see that there are two modes, and they almost match the two solutions of the deterministic system. So as we increase the system size, what happens to the probability distribution? How do they match, right? How does the probability distribution match the solutions of the ordinary differential equation, right? So there will be kinetic constants, right, for which we will start with a bimodal distribution. And here we recast the system in terms not of numbers of molecules, right, but of concentrations of X. So that we keep the same concentration. We increase the volume, so we also increase proportionally the number of molecules, so that we always have the same concentration. And we can discuss this in depth of system sizes. So here we have a volume of 1. This is a reduced type of units that we use. And we have small volume. We have a bimodal distribution. It's not prominent, but it's there. As we increase the size of the system, right, the bimodality is lost. we see just a single probability distribution, right, that is Gaussian, and then as we increase the system size, it starts becoming delta-like function. Okay? It is only, though, on the left solution of the deterministic system, right? We lose the right-hand side solution. And again, people have observed this, right, 20, 30 years ago, right, with Xian being, you know, just more recently discussing this in their work. Okay, so with ZI closure scheme, what we can do is really just do this, right? So we have the bimodal here in small volumes, and then go to enormous volumes, right, when the probability distribution really becomes a delta function, right, on the left-hand side solution of the deterministic system. Okay, so we can do this hundreds, if not thousands, of probability distributions are calculated there. You change the kinetic constant, right? This K4 that takes X, you know, like into the reservoir, takes X out. For small volumes, again, here we have a bimodal distribution. As we increase the volume now, the probability distribution goes to the right. Gaussian-like, you increase the system even more, becomes delta-like, okay? Delta-function-like. Again, we can do this a number of times. This is just the zooming in over here at this area, but then we can go to very large volumes, calculate the probability distribution. It is always a delta function on the right-hand side solution of the ODE.
Sorry, I missed this. So when does it go to the left and when to the right?
So this is the question that we're asking, right? When does it do it, right?
Yeah.
And are there cases, right, where for kinetic constant values, as you increase the volume, you will see both, right? So let me come back to this. So there are, right, values of K4. So for small volumes, right, there is a very wide range, right, of values of K4 where the probability distribution is bimodal. But as we increase the size of the system, as we increase the volume of the system, we see this range where bimodality is present just shrink. It keeps on shrinking and shrinking and shrinking. So we do see, you know, like even for large volumes, right, we do see bimodal distributions, right? It's two half delta functions ultimately that we come up with, right, at very large volumes, right? But this range of K4 values, where we see this bimodality, keeps on shrinking. And the one thing that tells us what happens is the entropy of the system. So we use the entropy, right, to close the scheme. So this is what happens at small volumes, right? As we increase this K4, we go from a unimodal to a bimodal distribution, right? And when you go from a unimodal to a bimodal distribution, what will certainly happen is that the entropy of the system will increase. Right? That's the variance will increase, the third order moment will increase, the fourth order moment. So the entropy that you calculate as you increase K4 and you go from unimodal to bimodal increases, right? The entropy will reach a maximum over here. So this area here, right, is where we see bimodal distributions. It reaches a maximum when the two modes are almost, you know, of identical significance, I'll say, size. And then as you move K4 even more, it goes from bimodal to unimodal, right? And the entropy starts decreasing at that point. As I said, what happens as we increase the volume is that this range of bimodality, right, just shrinks, right? There is, and this is a conjecture here, at the thermodynamic limit, there will be just a single value of K4, right, using the stochastic system, a single value of K4 where you're going to have the two solutions. So really, at the thermodynamic limit, the stochastic model will match the deterministic one, right, the two solutions, only for a single K4, right, this singular point. Let me finish here with just ultimately a question, and I'll go back, you know, like to canonical statistical mechanics, you know, equilibrium states. Equilibrium states, by the way, for chemical engineers, physicists, and chemists, right, is not always the same as equilibrium for mathematicians. Equilibrium for us has a strict physical meaning. Equilibrium is a system is at equilibrium when there are no gradients in the temperature, the pressure, and the chemical potential within it. When there are no gradients in T, P, and nu, there is no transfer, there's no transport of mass, there's no transport of energy within the the system. That is at equilibrium. And then, right, statistical mechanics, right, suggests that the number of microscopic states that becomes available when you have an equilibrium system is maximum, right? The Boltzmann entropy, right, calculated with the number of microstates is maximum. The Gibbs entropy, right, is also maximum. And it was a postulate, right, that Boltzmann and Gibbs made that the number of microscopic states is going to be maximum at equilibrium, that the entropy is going to be maximum. That indeed, leads to all known equilibrium state properties consistent with thermodynamics. So here we're not discussing equilibrium states. I mean, we're talking about steady states, right? The system is now open. It's still isochoric, right? It's still isothermal. But now what we really do is we place the Slogel model, for example, right? This is what I'm talking about here. We place it between two reservoirs, right? So there is a gradient, right, of chemical potentials, and within the system, the reactions take place in there, taking care, of the transport of mass, right, from the higher chemical potential to the lower chemical potential reservoir, right? There's a steady state that is reached in here, okay? And we always find the correct steady state, right, by postulating that the entropy, the Gibbs entropy of the system is maximum. We use this, of course, numerically, right, just referencing Shannon's information entropy. But physically, right, there's a system, it has a state space, the system distributes itself in that state space, right, with a probability distribution that maximizes the Gibbs entropy. So we're wondering whether indeed systems at steady state reach their steady state, also maximizing their Gibbs entropy. So to summarize and close, we have a way that for simple toy systems we can calculate probability distributions for non-linear reacting systems away from the thermodynamic limit. We can have tools now that start allowing us to run stability analysis not in a dissimilar way to the analysis tools that are available for deterministic systems. We can calculate eigenvalues. And then the question, right, that is still open to us, right, and it's going to take a long time for us to answer in the positive or in the negative, is whether indeed chemical reaction systems attain a steady state reaching a maximum entropy. And with this, I'll thank you for your attention.
Related to your last point, so would you say at any moment closure or order, like let's say you pick 3 for some system, would you say that I would be the optimal moment closure scheme in terms of reducing error, or you don't have that claim?
So there will be a point, right, beyond which adding more moments will add nothing to the accuracy of the calculation.
But you wouldn't say if you fix the, or like let's say you want to stick to just first and second moment, you wouldn't prescribe using the ZI closure as the best.
No, because the results would be wrong then, right? I mean, if you try the Slogel model,
of course the results would be wrong. You will have some error, but you would, if you were like, if for some reason you had to kind of keep your approximation to that level, would you say the ZI closure would be the best approximation compared to any other kind of closure scheme?
Oh, it's still wrong, right? And whether you're asking me whether it's less wrong than other methods.
I mean, it's always approximation, right?
I do not know. I cannot answer this question. Yeah, Sandro.
So,
Go ahead.
No, sorry. I didn't realize. I'll go.
You have, when you look at different parameters, for example, killing the Slogel or whatever, am I right in saying that depending on your parameter space, the number of moments that you need to approximate depends on the region that you are looking at?
So yes, in principle, yes, the Slogel model, right? I mean, there will be kinetic constant values for its unimodal, and 2 moments will suffice. as we go into higher volumes, right? Even when K4 for small volumes gives us bimodal, right? It becomes a unimodal again.
Yes. So, because you agree, then I ask, when do you know what is the minimum number of moments that you have to pick?
Yeah, I do not know a priori. I do not know at this point. What we have done when we do not run SSAs, right, to just figure things out briefly, we can just do this empirically. Go to 8, go to 10, and if 10 does not give us anything better than 8, we'll continue with 8. There is a danger, right, and this goes back to the limitations of using this for exploring dynamics, that the system, right, will move from a region where the probability is unimodal to one that is bimodal. And then we're still using 2 or 4 moments in there. That's not going to cut it.
Just 2 short questions. For the Schlegel, why not take as your initial distribution the sum of 2 delta functions?
We could. We have.
And wouldn't that speed up the behavior quite considerably?
It does.
Yeah,
It does.
That would be an obvious thing to do, right? So.
Right. So, I mean, again, if we have any information.
Well, you have information.
We do, of course. For Schlegel model,
why not use it?
for the Schlegel information, we have an analytical solution, of course, right? So,
I
yes.
don't use the analytical one. It's 2 delta functions, right? Instead of the 1.
Yes, we do that. We do that. So, I mean, it does not make sense to start with a uniform distribution.
And the second question is this behavior of the relative mass about the 2 equilibrium points. Isn't this a function of the initial concentration of molecules? And so if you started off with initial values near 1 mass.
No, this is the interesting thing, right? So when we get the left solution, right, we will make sure that there will be simulations where we start from the right one, just dead on the right one, right? And we'll do this with the ZA closure scheme, and we'll do this with SSA, right? And it's interesting to see, ZA closure scheme will just move to the left immediately, right? It's interesting to see the SSA, right? And I was not believing this yet. I was hesitant yet to believe this, but you start on the right solution, and then all the trajectories fall on the left solution. And ultimately, they maximize the entropy. That's all I can say right now. That's interesting. Yeah.
Maybe a last question, and then
And so, of course, the ideas using moment closures and maximum entropy closures for the unresolved moments. You can see that in liquid systems, turbulence, neuroscience. People use that. So my question is, and these are all very different systems in chemical reaction networks, of course. So my question is, are there things about the dynamics of chemical reaction networks that make these closure ideas work better than in some other systems, or are there particular things that make things more challenging that you had to sort of devise things to overcome things that were easier in some of the other systems?
I do not know. I will say this. I hope, right, that at steady state, indeed, systems attain the distribution that maximizes the entropy. And when this is true, from a physical point of view, then it's only natural to use an entropy maximization scheme to find the probability distribution. But I can't answer this definitely at this point.
thank the speaker again.